Tesla's rapid growth in Austin signals more than simple expansion, with employment at Gigafactory Texas nearly doubling to around 23,000 workers by late 2023. Many believe Tesla has been quietly preparing for its next major step. Many industry analysts now see the long-awaited Model 2 as Tesla's next big step. Early reports suggest a starting price of just $9,875, paired with axial flux motor technology, a compact, efficient design that promises stronger performance at a lower cost. With production power anchored in Texas, the Model 2 could mark the true beginning of Tesla's push to make EVs affordable for the masses. But what exactly makes the 2026 Tesla Model 2 such a shock to the market? Is it the ultra-low price, the next-gen battery tech, or the design choices that break away from tradition? And, more importantly, would it be worth enough to you? We'll break it down all in today's video. Welcome back to Autogearshift, the place where Tesla's next moves are broken down with hard numbers and real-world impact. In this video, you might notice that some numbers, prices, or specs shift compared to earlier reports. That's because as we dig deeper, new details surface, and we update our coverage so you always get the most accurate picture possible. And before we get into it, we're closing in on our next milestone, 6,789 subscribers. Each one helps us cut through the noise and deliver fact-based Tesla coverage you won't find anywhere else. So if this analysis is what you're here for, hit subscribe and turn on notifications. It really makes a difference. 1. Have you ever noticed how the real strength of an EV lies in its motor and how this new motor could be the key to Tesla's Model 2? Axial flux motors represent a new generation of electric motor design that could play a central role in Tesla's upcoming Model 2. Unlike traditional radial flux motors, where the magnetic force flows outward from the center in a cylindrical shape, axial flux motors channel magnetic energy along a flat disc-like structure. This key difference results in a motor that is much thinner and more compact, earning it the nickname pancake motor. Structurally, an axial flux motor typically consists of two flat stators, with copper windings placed on either side of a central rotor containing permanent magnets. This layout creates a larger active surface area for generating torque, while keeping the motor's thickness to a minimum. While a typical radial motor might be large and bulky, measuring hundreds of millimeters in length, axial flux motors can be as slim as 50 to 100 millimeters thick, compared to the 200 to 300 millimeters of bulkier cylindrical motors, while still delivering equal or even greater power output. The practical impact of this compact design is significant. By switching to axial flux motors, Tesla is not just saving space, it is setting up Model 2 for better performance, improved efficiency, and more flexible vehicle design. For example, axial flux motors can deliver between 30 to 50% more power for their size and weight compared to conventional motors. A motor weighing around 20 kilograms could generate up to 250 kilowatts of power, making it ideal for a smaller, more affordable electric vehicle like the Model 2 without sacrificing speed or acceleration. Because axial flux motors take up less space, Tesla engineers have more freedom to reimagine how the car is built. Instead of being limited by a large cylindrical motor in the center, the flatter pancake motor can be positioned closer to the wheels or tucked into tighter spaces, improving weight balance and handling. The flat shape also helps spread heat more evenly, reducing the risk of overheating during high-speed driving or long trips. In some tests, axial flux motors show up to 30% better heat dissipation compared to traditional motors, directly improving reliability and performance stability. From a production standpoint, axial flux motors offer real advantages as well. With fewer parts and a simpler structure that eliminates long shafts and extra support brackets, these motors are faster and cheaper to manufacture. Production costs could drop by 10 to 15% per motor once scaled up, which is key for Tesla's goal of offering the Model 2 at an entry price around $9,875. Do you think a smaller, thinner motor like this could really make a difference in how affordable and practical the Tesla Model 2 becomes? Comment axial flux below. If you believe this technology will help Tesla Model 2 lead the mass market EV segment. 2. How does axial flux motor technology help the Model 2 drive farther, accelerate faster, and waste less energy with every mile? The adoption of axial flux motor technology in Tesla's Model 2 is expected to deliver clear improvements in both driving performance and energy efficiency that drivers will notice immediately. One of the most important benefits is extended driving range. Thanks to higher efficiency levels, axial flux motors convert between 96 to 98% of battery energy into usable motion, compared to around 92 to 94% in traditional radial motors. While this percentage difference may seem small, over long distances it adds up significantly. For example, in a vehicle targeting 300 miles per charge, this improved efficiency could extend the range by an additional 15 to 20 miles. Instant torque is another major advantage. Axial flux motors have a shorter magnetic path and flatter construction, allowing them to deliver torque more directly and with faster response times. This results in sharper acceleration, especially at lower speeds where electric vehicles naturally perform well. For Tesla's Model 2, this means quicker 0 to 60 miles per hour times and smoother responsiveness in everyday driving situations, whether navigating city streets or merging onto highways. Reduced energy loss is also a key factor. The compact, flat design of axial flux motors helps minimize heat generation during operation. Because less energy is wasted as heat, more of the battery's stored power goes toward actually moving the car. In addition, lower heat production helps reduce the strain on cooling systems, which can contribute to better long-term reliability and reduced maintenance needs. Finally, regenerative braking is more effective with axial flux motors. Their precise magnetic control allows for smoother and more efficient energy recovery when slowing down. This means a greater percentage of kinetic energy is recaptured and sent back into the battery, helping to extend range even further. Industry estimates suggest regenerative braking systems paired with axial flux motors can improve energy recovery efficiency by 10 to 15% compared to older motor designs. 3. Have you ever considered how Tesla's Model 2 could look and handle differently thanks to the compact shape of its new axial flux motor? The introduction of axial flux motor technology is also expected to have a direct and visible impact on the driving experience of Tesla's Model 2. Axial flux motors use a 50 to 100 millimeters thick, disc-like pancake design, which allows Tesla to build the Model 2 with a lower ride height, helping the car sit closer to the ground. A lower ride height does more than just give the car a sportier appearance. It improves aerodynamics, making the vehicle glide through the air more easily. According to industry data, even lowering a car by just 20 to 30 millimeters can reduce air resistance enough to increase driving range by 5 to 7% more without needing a bigger battery. This design change also helps the Model 2 maintain a modern, sleek look while supporting better energy efficiency. Beyond aerodynamics, the compact size of axial flux motors gives Tesla engineers more freedom in how they position the wheels and suspension. With no bulky motor taking up space, they can move the wheels closer to the car's corners, which increases stability on the road. It also frees up more interior room for passengers and cargo. For a smaller car like the Model 2, where every centimeter matters, this flexibility can make the cabin feel noticeably more spacious while improving how the car handles in turns or quick lane changes. Another design benefit comes from the simplified body structure. Because axial flux motors take up less room, there is no need for large motor housings that stick out or interrupt the car's smooth lines. This allows Tesla to shape the exterior in a cleaner, simpler way, further reducing drag and improving both looks and efficiency. Lastly, weight distribution sees a real improvement with axial flux motor integration. These motors are generally 10 to 20% lighter than traditional designs. By placing lighter, flatter motors closer to the car's center of gravity, Tesla can balance the Model 2 more evenly between the front and rear. This helps the car feel more responsive during cornering, braking, or quick direction changes, especially important for city driving. Do you think a more compact, thinner motor like this could really help the Tesla Model 2 look sleeker and handle more easily in city traffic? Comment, Model 2 wins, if you are tired of struggling with city driving. 4. Have you ever thought about how Tesla's Model 2 could feel more spacious and easier to use, all thanks to the compact design of its new axial flux motor? The introduction of axial flux motor technology is set to transform not just how Tesla's Model 2 performs, but also how it feels inside for both drivers and passengers. One of the clearest changes comes from the increased cabin space. Axial flux motors are designed to be much more compact than traditional radial motors. While a typical radial motor might occupy around 70 to 90 liters of space under the floor, an equivalent axial flux motor takes up only about 50 to 65 liters. This reduction in motor volume by up to 30% allows Tesla to create more room for passengers and cargo. In a compact car like the Model 2, that extra space translates into larger rear legroom, expanded trunk capacity, and more thoughtful use of every inch inside the vehicle. A major advantage of this compact motor design is the ability to create a completely flat interior floor. In many electric vehicles, even today, small floor bulges or tunnels are left over from the way motors and drivetrains are positioned. Axial flux motors' slim profile means Tesla can offer Model 2 owners a perfectly flat floor from the front seats to the back, increasing foot space by 30 to 50 millimeters for rear passengers. It also opens up new options for storage compartments under the floor and more flexible seating layouts. That flexibility extends to how the seats themselves can be arranged. Because there are fewer mechanical parts taking up space beneath the cabin and around the motor housings, Tesla designers can experiment with features like sliding rear seats, fold-flat front seats, and multi-position cargo dividers. These layout choices, which are often limited in smaller vehicles, can increase usable cargo space by 10 to 15% and help drivers adapt the interior depending on whether they need more passenger seating or more room for luggage. Another subtle but important benefit is a lower step-in height. With a flatter motor and less underbody bulk, Tesla can design the Model 2 with a ride height lowered by 20 to 30 millimeters without affecting ground clearance needed for city roads. This makes entering and exiting the vehicle easier for everyone. Research shows that even a 20 millimeter drop in step-in height can reduce the physical effort required by around 5 to 8%, making a difference especially for children, seniors, or anyone carrying heavy bags. 5. How is Tesla using axial flux motor technology to make the Model 2 not just more powerful, but also more affordable, reliable, and ready for the future? Axial flux motor technology is not only about improving performance and design for Tesla's Model 2, but also about delivering key manufacturing, reliability, and sustainability advantages that support Tesla's long-term strategy. One of the most direct impacts is on reduced manufacturing costs. Axial flux motors have a simpler, flatter construction with fewer components compared to traditional radial motors. This streamlined design eliminates long shafts, complex brackets, and excess material. As a result, production becomes faster and less expensive. Industry estimates suggest axial flux motors can cut motor production costs by 10 to 15% per unit. For Tesla, this efficiency is essential to achieving the Model 2's projected $9,875 starting price while maintaining healthy margins. Improved reliability is another clear benefit tied to the axial flux structure. With fewer moving parts and a naturally lower operating temperature due to better heat dissipation, axial flux motors reduce wear and tear on components over time. This translates into longer service life and fewer mechanical failures, an important factor for a high-volume mass-market car like the Model 2, where maintenance costs need to be as low as possible. Scalability also becomes more achievable. Because axial flux motors are easier to assemble and require less specialized tooling, Tesla can scale up production more smoothly at facilities like Gigafactory Texas, where vehicle output is expected to grow dramatically. This aligns with Tesla's broader strategy to produce millions of affordable EVs per year while minimizing factory complexity. In terms of future-proofing, axial flux motors provide a flexible platform for upcoming Tesla vehicles beyond the Model 2. Their compact form factor and high efficiency make them adaptable to various sizes and vehicle types, from compact sedans to light commercial vehicles. By standardizing this motor architecture, Tesla ensures its future lineup remains competitive as EV technology evolves. Finally, there is the environmental impact. Because axial flux motors convert more of the battery's stored energy into forward motion and waste less energy as heat, they contribute to a smaller carbon footprint per mile driven. Additionally, using fewer raw materials in motor construction reduces environmental strain during manufacturing. Taken together, these advantages position axial flux motor technology as a key enabler of Tesla's long-term goals, making electric vehicles more affordable, more reliable, and more sustainable on a global scale. Everyone thinks EV battery progress is about faster charging and more range. But what if Tesla just proved the real secret, getting power out instantly? In 2025, a hidden Tesla lab leaked plans for quantum pulse, some aluminum-ion breakthrough unleashing 7,000 watts per kilogram, which is insanely 10 times lithium's specs. No power fade, no heat throttling, and a crystalline lattice that thrives at 85 degrees Celsius for 10,000 plus cycles. Now imagine a Tesla Model 2 out-accelerating a Porsche, charging to 80% in 5 minutes, and built without a single China-controlled mineral. How can Tesla make it? What's ending China's $400 billion battery empire? 1. How does Tesla redefine EV power with quantum pulse technology? Everyone obsesses over how fast an electric vehicle can charge, but here is the secret Tesla engineers have uncovered. The real bottleneck has never been about getting energy in. It has always been about getting energy out fast enough. Imagine pressing your foot down and feeling a surge so intense it feels like a rocket launch every single time you hit the accelerator. That is exactly where Tesla's new aluminum-ion battery and its groundbreaking quantum pulse technology step in, and the numbers behind it are test bench proof. For years, even the best electric vehicles have suffered from what engineers call the power fade. Take the Tesla Model S Plaid as an example. On paper, it promises 1,020 horsepower, but that output only lasts 2.3 seconds before the battery temperature climbs to 45 degrees Celsius, forcing the system to cut power by up to 40%. That means your breathtaking 0 to 60 accelerations of 1.99 seconds only happen once, and then you wait 20 minutes for the pack to cool enough to do it again. This is a drawback of lithium chemistry. Inside those cells, lithium dendrites form under high discharge, creating resistance. Electrolytes break down under extreme current, microfractures spread, and each power burst creates heat that weakens the next. It is a downward spiral baked into the old way of building batteries. Tesla's quantum pulse technology rewrites that script. Instead of forcing a battery to deliver a continuous heavy drain it cannot sustain, quantum pulse fires microbursts of controlled energy. Testing shows an estimated 7,000 watts per kilogram compared to 500 watts per kilogram in today's lithium cells. And how insane is the result? A compact Model 2 that launches from 0 to 60 miles per hour in 3.2 seconds. That's faster than a Porsche 911, yet costs around just $15,759. That is precision engineering with a real measurable output. Does this trim blow your mind? Drop the number 3.2 below if this is truly the new leap in battery technology. And stay tuned. We will show you how specifically Tesla did it. The reason it works is deeper than just new chemistry. Aluminum ions do not build dendrites. They organize into crystalline lattices that actually grow stronger under repeated use. Lab data shows power consistency staying at 100% across more than 10,000 full throttle discharge cycles. Even better, these cells prefer heat, operating optimally at 85 degrees Celsius, where lithium would be throttling itself down. This is not fragile tech. It is robust enough to handle the extremes of American summers and the demands of heavy-duty use. Adaptive power scaling takes it even further. Traditional batteries dump the same output, whether you are creeping through city traffic or merging onto an interstate. Tesla's aluminum ion pack reads conditions in real time, cutting energy waste by 15%. Picture cruising calmly and your Model 2 barely sipping power, then stomping on the pedal and feeling a tsunami of torque pour through instantly. And that power holds even under brutal conditions, including towing 5,000 pounds or climbing 10% grades, while lithium cells would be losing 20 to 30% efficiency. Tests show aluminum ion packs holding 95% efficiency in 90-degree Fahrenheit heat compared to lithium's 80%. Then come the exclusive numbers that sound impossible until you see them in action. 15 back-to-back ludicrous mode launches with zero degradation, unlimited laps in track mode without thermal throttling, and towing 15,000 pounds uphill without a single power dip. The same battery can dump 2 megawatts of energy instantly, which is enough to power 200 homes, or run a 400-amp welding rig for 8 hours straight. And what about regenerative braking? It captures 98% of energy, turning downhill driving into a 15 to 20% range increase instead of a drain. No other electric vehicle battery on Earth claims a pulse delivery system like this. Tesla is not just improving batteries. It is rewriting the fundamental relationship between driver and machine. Model 2 becomes something out of science fiction, a car that feels alive, a thrill machine every time you drive it. Would you even believe it until you saw it yourself? Comment below with the words "arrives here" if this blows your mind and you're ready to be part of the first wave to witness this breakthrough. And if you think that power delivery is wild, wait until you see what Tesla has done with charging speed. Let's dive into why these new batteries can charge faster than you can pump gas. 2. Why can Tesla's new batteries charge faster than you can pump gas? What if charging your electric vehicle was faster than filling your coffee cup? That is no longer a fantasy. It is exactly what Tesla's new aluminum ion battery is engineered to do, and the numbers are staggering. At the heart of this breakthrough is something called the hypercharge nanolattice, a microscopic structure inside each cell that lets aluminum ions move 10 times faster than lithium ions ever could. The result is a verified charge rate that takes the battery from 0 to 80% in just 5 minutes on a Tesla Supercharger 5.4. That is less time than it takes most people to grab a coffee on their way to work, and far less time than you would spend at a gas pump on a busy morning in Texas or New York. You have said it over and over for years. I would buy an electric vehicle if charging were as fast as pumping gas. Tesla listened. This is not hype. According to a 2025 market survey, 65% of gas car owners admitted they would switch to EVs if the charge time dropped under 10 minutes. By delivering an 80% charge in 5 minutes, Tesla's technology has the potential to convert 40% of those drivers instantly. That is not marketing talk. That is a documented behavioral shift backed by data from thousands of drivers across America. And it is not just about speed, it is about resilience. Traditional lithium batteries slow down when the weather is too hot or too cold. The hypercharged nanolattice is different. Its design dissipates heat 50% faster than lithium, so even if you are charging in 100 degrees Fahrenheit under a blazing Arizona sun or in freezing Minnesota snow, your Model 2 will accept that charge without flinching. This is real engineering solving a real problem that drivers have complained about for years. Then, think about what this does to the global balance of power. Right now, China's fastest charging vehicles, like the Xpeng G9, take 18 minutes to reach a comparable charge. That is impressive by yesterday's standards, but next to Tesla's 5-minute result, it feels like ancient history. If Tesla scales this across the globe, analysts project it could cut into China's 50% hold on the electric vehicle market by 2030. China's cars might be fast, but Tesla is playing in a completely different league. Imagine pulling into a supercharger, plugging in, and driving off before your playlist even gets to the chorus. This is not just faster charging, it is the death of range anxiety forever. This is the future you have been begging for, and it is arriving right in front of you. If that does not give you goosebumps, keep watching, because what Tesla has done next will absolutely blow your mind. 3. How will Tesla revolutionize battery production and distribution intensively worldwide? Leaked internal documents show Tesla's Gigafactory 2.0 concept is nothing short of staggering. Each new facility is designed to produce 500,000 aluminum-ion battery packs every year, which is 10 times the output of today's gigafactories, while taking up only 1/3 of the footprint. And with 97% of the process run by robotics, human hands only step in for quality control. These are not distant ideas on a whiteboard. 12 new facilities have already been confirmed for 2025. 35 are slated to be operational in 2026, and projections show over 100 facilities reaching every major market by 2027. But Tesla is not stopping there. Their speculative global battery swarm model is the kind of idea that makes competitors sweat. Imagine micro-gigafactories set up in 20 countries by 2027, each capable of producing 1 million aluminum-ion packs every single year. This scale is not just impressive, it drops production costs to around $40 per kilowatt-hour compared to $120 per kilowatt-hour for traditional lithium-ion. That slashes the Model 2's production cost by 25%, making a car with supercar performance cost less than many used sedans in America. The supply chain behind this revolution is just as groundbreaking. Tesla's AI systems are designed to optimize aluminum sourcing, which is an element 10 times more abundant than lithium and recycle 95% of materials right on site. That means no dependence on China's lithium refining, which currently controls 80% of the global market. Analysts estimate aluminum-ion production could save Tesla $10 billion annually by 2030 compared to the volatile rare earth supply chains others still rely on. That is hard math, not wishful thinking. And the ripple effect goes far beyond cars. Tesla is bundling these aluminum-ion cells into home power walls and grid-scale megapacks, creating a unified energy platform. By 2028, Tesla's ecosystem could power 5% of global electricity demand. This is no longer just about selling vehicles. This is about owning the energy future itself. The way Tesla plans to get these batteries into your hands is just as bold. Picture a direct-to-consumer 3.0 experience where you order your car and have it delivered anywhere on Earth within 72 hours through a Gigafactory Express. Imagine choosing from 847 million possible configurations and having a Tesla semi-truck deliver your car straight to your driveway. Then consider the subscription model. Buy the car for $8,000 and lease the battery for $99 per month, or buy the complete car for $15,000 and even swap to the newest battery tech every year for just $15,759. That is not a sales gimmick. That is Tesla redefining ownership itself. And here is the part that keeps executives in Shenzhen awake at night. Giants like KTL and BYD are deeply invested in centralized lithium supply chains and lack the AI-driven, decentralized scale Tesla is building. Industry analysts project China's $100 billion battery sector could lose 30% of its market share by 2030. Tesla is not just building batteries. They are building an empire, a supply chain, and a future that no one else can match. Do you believe a network of micro-gigafactories across 20 countries could really shake up a $100 billion industry overnight? Drop "end of China" if you think so. 4. Why will the 2026 Model 2 spark a global EV frenzy? Could a single car make gasoline obsolete for billions? Tesla's answer is a bold yes, and the numbers back it up. The new Model 2 offers an incredible 550 miles of range, a 5-minute charge time, and the same quantum pulse performance we just explored, making it an obvious choice over any gas car on the road today. Compare that to something like BYD's Dolphin at $21,000, giving only 200 miles and a 25-minute charge. Suddenly, the Model 2 is in a league of its own. Tesla is not just selling a car, it is triggering mass adoption. Internal projections show 4 million Model 2 units sold every year by 2030, capturing 20% of the global market. That could drive electric vehicle penetration to 30% by 2030, up from 12% in 2025. For perspective, electric vehicles already saved 1.5 billion gallons of gas in 2024. With Model 2 scaling up, that number could triple in just a few years. This is built on real innovation, like the aluminum ion's self-healing electrolyte, which repairs microdamage during use and is expected to last 500,000 cycles, which is actually over 100 years of driving. That durability, combined with a price of just $15,759, makes it just as appealing in places like India or Africa as it is in Los Angeles or New York. In cities like Mumbai or Lagos, this is more than a car. It is independent from fuel costs that have drained wallets for decades. This is the car you've dreamed of: affordable, lightning fast, and unstoppable. The Model 2 is not just a vehicle, it is a movement. How promising is it? Please drop just a word below to describe your feelings to us. We're so eager to hear your emotion. Think about it. When was the last time you felt that jolt of "this changed everything"? If that hits you tonight, don't just click away. Smash that subscribe button on your channel to see a new era coming. And thanks for watching. Elon Musk just shocked the entire automotive world when he confirmed something never seen before in a budget Tesla: a 0.9 meter gap in the all-new 2026 Tesla Model 2's chassis design. Some are cheering, some are panicking, some are whispering, is this stitched-together frame going to snap when it matters most? But do you remember what Musk declared?
It's actually not just a revolution in vehicle design, but a revolution in vehicle manufacturing.
Actually, revolutions come with doubt, and this gap has sparked one of the biggest safety debates Tesla has ever faced. And today, we are diving right into it with all exclusive testing specs proving this strange, futuristic chassis is stronger than any traditional welded frame you've ever known. 1. Why did Tesla choose megacasting over traditional welded frames? Why would Tesla abandon traditional car building for a radical new approach? The answer lies in something most people never think about when buying a car, but it could be the difference between life and death. Here's what the automotive industry doesn't want you to know about how your current car is actually built. Every traditional vehicle rolling off assembly lines today is essentially 400 separate stamped metal pieces welded together with thousands of individual welds. Take a standard sedan. Engineers estimate it contains roughly 400 stamped components, held together by 1,600 separate weld points. That's 1,600 opportunities for failure, 1,600 potential weak spots in the very structure designed to protect your family. The mathematics is terrifying when you break it down. Each individual weld carries a failure risk of approximately 0.5 to 1% under extreme stress conditions. Multiply that by 1,600 welds, and you're looking at a cumulative structural vulnerability that would make any engineer lose sleep. But here's the real kicker. Those thousands of welds don't just compromise safety, they're bleeding money from every vehicle. Each car spends an additional 2 to 3 hours in production just for welding operations, adding $500 to $1,000 to the manufacturing cost that ultimately gets passed directly to you, the consumer. Imagine a car held together by thousands of tiny weak spots. Does that sound reliable to you? This is exactly why Tesla's engineering team made a decision that sent shockwaves through Detroit, New York, and London. Tesla completely flipped that playbook with their mega casting revolution. Instead of hundreds of pieces welded together, Tesla deploys massive 6,000 to 9,000 ton presses, which are machines so large they require their own buildings, to die-cast the front and rear underbody sections as single, solid aluminum alloy pieces. We're talking about reducing 400 separate components down to just 2 or 3 major structural castings. The production impact is staggering as the assembly time drops by 30%, and manufacturing costs plummet by up to 40%. That translates to an estimated $5,000 to $7,000 in savings per Model 2, which is precisely what makes that sub-$25,000 price tag mathematically possible. But here's where the 0.9 meter gap revealed becomes absolutely crucial to understanding Tesla's engineering genius. Traditional automotive thinking says more welds equal more strength through redundancy. Tesla's engineers discovered the opposite was true. They now use front and rear sections cast as giant aluminum structures, each measuring nearly 0.9 meters across between critical mounting points and joined together by the battery pack acting as a rock-solid structural floor. This 0.9 meter gap represents the critical connection zone where front casting, rear casting, and battery pack unite as a single rigid structure. Instead of 1,600 potential failure points, you now have exactly 3 major structural connections, each engineered to handle forces that would destroy traditional welded joints. The weight difference is truly revolutionary engineering, as Musk has stated. A traditional underbody constructed from 400 separate parts weighs approximately 270 kilograms. Tesla's megacast design, only 198 kilograms, showing a 27% reduction in structural weight. That means faster acceleration, extended driving range, and most importantly, far fewer joints that can fail over time. When you eliminate 72 kilograms of unnecessary structural weight, you're not just improving performance, you're fundamentally changing what's possible in automotive design. This isn't just about building cars faster, it's about making EVs so affordable that anyone can own one. For families earning modest incomes, those $5,000 to $7,000 in manufacturing savings represent the difference between electric vehicle ownership and being stuck with gas-powered transportation for another decade. When federal and state subsidies combine with Tesla's manufacturing cost reductions, we're looking at Model 2 prices dropping below $25,000, finally putting sustainable transportation within reach of middle-class American families. If you knew your car's entire frame was built from hundreds of pieces with thousands of tiny welds, would that make you feel safe? Or would it make you nervous every time you hit a pothole? Drop your thoughts below and type the words megacasting in your comment so I can see how many of you are ready to embrace this bold design shift. 2. How extremely strong is the 0.9 meter gap compared to traditional welding? How can fewer connections create a safer car? That sounds impossible, right? Yet this is exactly the science behind Tesla's mega casting strength. And it is not just theory. It is backed by real engineering data. For decades, American automakers convinced us that more welds meant more safety through redundancy. But Tesla's engineers discovered something that traditional manufacturers either missed or deliberately ignored. The fundamental weakness wasn't in having too few connections, but in having thousands of inferior ones. The science behind mega casting strength reveals a materials revolution that makes traditional automotive aluminum look like child's play compared to what Tesla has developed. Tesla's proprietary aluminum alloys achieve yield strength ratings between 140 and 175 megapascals, combined with electrical conductivity ranging from 45 to 55% international annealed copper standard. Compare that to traditional automotive aluminum, which typically maxes out between 90 and 120 megapascals yield strength, and you're looking at a shocking reality. Tesla's casting aluminum delivers 40% greater structural strength than standard automotive aluminum used by every other manufacturer. These are metallurgical specifications that determine whether your car's structure holds together or collapses during a crash. But here's where Tesla's 0.9 meter connection engineering becomes absolutely revolutionary. Instead of traditional welding that creates tiny 2mm bead widths as connection points, Tesla employs aerospace-grade structural adhesive combined with high tensile bolts rated at over 1,200 megapascals tensile strength. During assembly, these connections experience 15 to 20 tons of clamping force, which is equivalent to 30,000 pounds pressing two massive aluminum pieces together until they become virtually inseparable. The bond surface area created by that 0.9 meter connection spans 2.7 square meters compared to traditional welding's minuscule 2mm bead width. We're talking about over 1,000 times more surface areas distributing stress loads. The real-world strength data proves this isn't just theoretical engineering. It's measurable superiority that translates directly into passenger safety. Tesla reports 30% higher torsional rigidity compared to Model 3's traditional construction methods, meaning the entire vehicle structure resists twisting forces that would compromise passenger compartment integrity in traditional cars. Simultaneously, the chassis achieves 20% weight reduction, dropping from an estimated 225 kilograms for equivalent steel frame construction down to just 180 kilograms. That 45 kilogram weight savings doesn't just improve acceleration and range, and, more promisingly, it represents 45 kilograms less mass that needs to be controlled during emergency maneuvers. The manufacturing efficiency reveals just how superior this approach really is. Traditional stamping and welding operations require 6 hours of production time per vehicle chassis, with multiple quality control checkpoints to ensure those 1,600 welds meet safety standards. Tesla's mega casting process completes the entire front or rear section in 10 minutes of casting time plus assembly, a 36-fold improvement in production efficiency while simultaneously creating structurally superior results. Think about what this means for American families buying their next vehicle. You're not just getting a car that's built faster and costs less. You're getting a vehicle whose fundamental structure is engineered to standards that exceed traditional automotive manufacturing by margins that would have been impossible just 5 years ago. When crash forces hit that 0.9 meter connection zone, they encounter aerospace-grade materials and bonding techniques, distributing loads across surface areas measured in square meters rather than millimeters. This is why every major automaker is scrambling to reverse engineer Tesla's mega casting technology, because they finally understand that traditional welding methods are becoming obsolete. And knowing that Tesla's proprietary alloy is 40% stronger than the aluminum in most cars on the road today. Do you feel more confident trusting this design when your family is riding inside? We really want to hear what you think, so drop your thoughts below and type the words 0.9 meter in your comment to show me you are following every detail of this breakthrough. And now, let's take this even further, because up next, you are about to see exactly how a so-called stitched-together chassis can end up being stronger than a single solid piece of steel. Stay right here. 3. How is a stitched-together chassis actually stronger than one piece of steel? Can a car with just a 0.9 meter gap hold up in a crash, or is it doomed to crack? That question has been fueling doubts everywhere, and I know exactly why. Stitched together sounds weak, right? But what if Tesla's method is actually stronger than anything we have seen before? Here's the truth. Tesla's high-pressure bonding system employs aerospace-grade structural adhesives with shear strength ratings of approximately 30 megapascals, which is the same bonding technology that holds commercial aircraft fuselages together at 35,000 feet. These adhesives work in conjunction with ultra-high strength bolts rated at 1200 megapascals tensile strength, creating connections that are literally stronger than the materials they're joining. The precision engineering behind this process uses laser-guided alignment systems that position castings with micron-level accuracy, completely eliminating stress concentrations that cause traditional welded joints to fail. Tesla's internal testing reveals numbers that should make every traditional automaker nervous. The Model 2 chassis achieves 35,000 newton meters per degree of torsional rigidity compared to the Model 3's 26,000 newton meters per degree, a 30% improvement in structural stiffness that makes the vehicle significantly less likely to twist or deform during crashes. These aren't theoretical calculations. Tesla conducted 40,000 virtual crash simulations, plus real-world impact tests at 64 kilometers per hour and 72 kilometers per hour. The results were stunning. The Model 2 chassis absorbed 25% more impact energy than the Model 3 while reducing cabin intrusion by 15%. This isn't a fragile patchwork, it's a fortress on wheels. The 0.9 meter gap represents deliberate engineering genius designed to maximize structural continuity rather than create weakness. The battery pack integration as a structural floor contributes an additional estimated 10,000 newton meters per degree of stiffness, roughly 20% more rigidity than traditional automotive designs can achieve. Tesla's approach mimics biomimicry principles inspired by human spine architecture. Rigid segments, represented by the castings connected through flexible, high-strength joints, represented by that 0.9 meter gap. This distributes crash forces evenly across the entire structure, preventing the localized failures that plague traditional welded construction. Your spine doesn't break because it has joints. It stays strong because those joints distribute loads intelligently across the entire skeletal system. Here's a surprising fact that proves this technology works under extreme conditions. Tesla's mega casting process underwent brutal stress testing in the Cybertruck, which survived off-road impacts at 50 kilometers per hour with zero structural damage to the casting joints. If the Cybertruck can handle that punishment, imagine what the Model 2 can do during typical road emergencies. For American families worried about maintenance costs, this engineering approach delivers financial benefits that traditional automakers simply cannot match. Megacasting reduces annual maintenance expenses by 20 to 30%, an estimated $500 to $1,000 less per year, because fewer parts mean fewer potential failure points requiring service. When repairs are necessary, Tesla's modular replacement techniques combined with aluminum welding capabilities mean minor damage costs approximately $200 to $500 compared to over $1,000 for equivalent traditional frame repairs. the repairability concerns that critics raise actually work in Tesla's favor. While individual castings are large, they're designed for straightforward replacement rather than complex reconstruction. Tesla service centers can patch minor casting damage using specialized aluminum welding techniques that cost a fraction of traditional bodywork. No more worrying about expensive repairs. This is a car built to last and save you money. What traditional automakers don't want you to understand is that Tesla's stitched-together approach represents the future of automotive construction because it's fundamentally superior to everything that came before it. The 0.9 meter gap isn't an engineering compromise. It's an engineering breakthrough that makes vehicles safer, lighter, more durable, and more affordable to maintain than anything rolling off traditional assembly lines. That's all for today's deep dive into the 2026 Tesla Model 2, a car that could truly change the EV game. This chassis is not stitched together to fail. It is stitched together to protect you and your family for years to come. If this breakdown gives you answers you have been waiting for, tell me what you think below. Do you trust this design now? Let me know in the comments by just one word, yes. And if you want to be part of the next big reveal, join our growing community by hitting subscribe and letting that bell quietly keep you in the loop. Stay tuned. Thanks for watching Auto Gear Shift. See you in the next one.